Yeah, I can hear you. Yeah. Ah, okay. Ah, yes, yes. Okay, I think if that you have to ask through the through the forum, yeah, because they will be in a better position to tell that those who are involved with the exams and all. Currently, I'm not involved there, so you can ask that doubt on the forum itself. They'll reply to that. Mostly, I think it will be given as in the question itself, if at all they have to ask in that sense. Yeah, otherwise they'll clear it there itself if you ask on forum. I think calculator. See, again, I will say you ask, but I what I remember for last year, I think calculator comes inbuilt in the when you attempt the exam online. The calculator is itself there. It's a scientific calculator. It's an Yeah, it's an online. Yeah, yeah. So I think the exam will be computer based exam. So they will be sending some link or something or like that, or maybe you have to visit some center to give the exam. Yeah, yeah. So if you have to go to the center, then obviously there will be a scientific calculator inbuilt. Yeah. Yes. Yeah, you can say the virtual calculator. So but again, I will say you ask through the forum. They will let you know the exact thing. Mostly they don't allow this calculator and all because it already comes inbuilt. Because nowadays electronic box are there, so there are calculator even watches also. Yes, 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 yes. Yeah, yeah. I hope there will be a mail from NPTEL side also before the exam. Okay, 1 or 2 weeks before the exam, explaining this. Uh, yeah, but it will be better if you can ask on the forum, especially about that deflection thing. Yeah, 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 sure. Yeah, 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 yeah. I know. Yeah, yeah. That was like internal exam for BTechs here. So for that, professor mentioned that. But for the NPTEL exam, like we have to inquire. Yeah, yeah, yeah. So we'll start today's session. Okay. So good evening all. So in today's session, uh, we'll go through some example problems on unsymmetrical banding and deflection of beams. And in the past week, you have gone through the lectures. So it consists of unsymmetrical bending, a brief introduction, because still it's a first level course kind of. So this strength of material. So derivation, a full derivation will be um, too mathematical right now. So professor has anyway given you the formula where for case of the unsymmetrical bending and what it means, he has told also that. So let's have a little recap of that and then we'll go to the questions. Okay. So uh, so uh, you know that there are two things. One is a symmetrical cross section and especially symmetry about the loading plane basically. So we usually load our load like this P. So there should be a symmetry about the vertical loading. So there is something called symmetrical section, or I will say cross section, and something is symmetrical loading. Okay, so these are two things. So by symmetrical section, as I told, they should one axis of symmetry, specifically vertical axis or vertical plane of symmetry. So you can see examples like this beams with such cross sections, also something like this. Okay, so it has a vertical plane of symmetry. Okay, then you can have a circular cross section also, it has a vertical plane of symmetry, and you can have a triangular also. Sorry, it does also have a vertical plane of symmetry, this kind of cross section also. Okay, so these cross sections you can have, and of course the rectangular or square cross section. So this is comes under the symmetrical cross section. Another thing is, so this comes under symmetrical cross section. Another thing is symmetrical loading. So if suppose I take a rectangular cross section, something like this, and you know that suppose this is a line of symmetry, I would say, or like I will call this as z axis, this is y axis, this is the centroid as well as the origin. So what happens, suppose if I put a load here, till now we were putting our load at this point, we were putting something like this P. Now I have put it somewhere else, not along the axis of symmetry. So this will also cause unsymmetrical bending, even though the section is symmetrical. Okay, even though the section is symmetrical, but the loading is not symmetrical. It is, the loading is not in the plane of symmetry. And if you go back and review the derivation of the pure bending Euler-Bernoulli theory or the pure bending theory, you will see that that's one of the postulate, that it says that the loading should pass through the plane of symmetry. Okay, so this will cause unsymmetrical bending. Okay, and if you have something, some unsymmetrical sections, like if you see angle section, so suppose like this, so suppose something like this. So in this you can see that its centroid lies somewhere here. So if I draw, you see that it is not symmetrical, it's an unsymmetrical section. So now even if you put your load at the centroid like this, as you have seen in the lecture also, how professor put a pen on an angle section and he pushes it. Okay, and you see that how if it is the load is applied at the centroid, it the angle section goes down, deflects in the downward direction, but also it twists. We have seen in the videos, in the presentation. Okay, and somewhere then what he does, he applies the same load, he puts a arrangement here and he applies the same load here, P, same load here. In that scenario you see that there is no rotation, of the cross section, but only it deflects downward and then it deflects away also. Okay, so if I draw a reference axis, I'll draw a reference, suppose this is my reference, this is the reference. So the this goes downward and it deflects something like this. So it bends in both, it bends in x as well, in y as well as z here. Okay, this is your z, this is y, correct. So here the loading you applied on the centroidal axis, but the issue is the centroidal axis is not symmetric axis, so it will cause unsymmetrical bending. So my point is we have to remember these two things: symmetrical cross section, symmetrical loading. Okay, if either one of this is not there, then the bending is going to be unsymmetrical. Okay, so that is there. So as I told, even if I in a symmetrical section, if I put loading here or if I put loading here, it is going to be subjected to unsymmetrical bending. Okay, so that is. And other way is, if I have an unsymmetrical section, even if I put the load on the centroidal axis, it passes through the centroid, it is going to be under unsymmetrical bending. Okay, but if in this specific case of a angle section, if we put load on the centroid, we saw that there is means apart from unsymmetrical bending, there was one more thing which was coming, that was the rotation of the cross section. And what happens when we put the load just very near to the edge, this edge, we found that there was no rotation, and that comes due to something called that comes due to something called shear center. I will just brief about it also. Shear center. Okay, so what is shear center? So it's a point through which, if the load is applied, the cross section of the beam does not undergo rotation. It does not undergo rotation. Okay, the cross section of the beam does not undergo rotation. Okay, so now what happens? I'll just give a short way. There is a proper way to find the shear center. To find shear center, basically you find the rotation in a cross section due to all the forces. Okay, basically when we learnt about the shear flow, which we saw in the case of shear. So when we learnt about shear flow, so basically we try to means equate shear flow in various members of the cross section with the applied load, and then we find what is those x and y. So basically we can find that x and y just by taking the moment at about any point, and we put that moment to be 0. Okay, so when we put that moment to be 0, and that this all I am doing in a cross section. Okay, so I'll just give a very small sense, like suppose there is some cross section is there. Okay, some cross section is there, so I'll have some shear flow happening, suppose something like this, and what I will do, I'll take a point, and then I will define those distances x and y of that point with respect to the forces, and then I find the total movement due to these shear flows and applied load about this point, and I put those as 0 because I have to make it as 0. Okay, and when I put that 0, I find these values of x and y, and those are the coordinates of actually the shear center. So there is a way to find shear center, but we as professor also has not dealt that in this, because it's a very first level course. We may not require it at this point of time, but we should know what is the concept of shear center. The concept is that if the load passes through the shear center, the cross section is never subjected to torsion, means torsion, you can say it's a torque happening. Okay, so it is not subjected to torsion. Now but I can give you a little bit thing, like how to locate or how to find in a particular cross section where the shear center will lie. So what it is that for doubly symmetric section, for a doubly symmetric cross section, shear center always lies on the point, or not on, at the point of intersection of the axis of symmetry. Okay, so if you have a cross section which is doubly symmetric, so I'll take example of a rectangular or a square cross section. So let's take an example of a rectangular cross section. Something like this. So you know that this is a doubly symmetric. So one is the z axis and another this is y axis. Okay, so you know about this z axis and about this z axis, it is symmetric this in this way, and about this y axis it is symmetric this in this way, the cross section. So what it tells, the shear center lies at the point of intersection of the axis of symmetry. So this is the point of intersection where the shear center lies. So the shear center and the centroid are same in rectangular or square or circular, because in all those cases the axis it is a doubly symmetric. Okay, so the shear center lies at the center. Okay, and second thing is, for singly symmetric, it's a quick way, means it's just a quick way, okay, anecdote kind of quick way to find or to locate the shear center. For singly symmetric cross sections, the shear center always lies on the axis of symmetry. Okay, so if your cross section is a singly symmetric, it's not doubly symmetric like square cross section or rectangular, so in that scenario the shear center will lie on the axis of symmetry. So let's have an example of this. So the best example for this is a channel, a C section we call also. So it's a symmetric cross section. So you know this axis, its centroid lies somewhere here. So this axis is not about this axis, we call it y. This cross section is not symmetric. However, about this axis the cross section is symmetric. So for this case the shear center lies here, because this z axis is the axis of symmetry. So shear center will lie here. Okay. Okay. So these two things, like just two points are there to just figure out where the shear center is. Okay. Okay. So that was we had gone in the unsymmetrical bending, and then I'll also say about the formula. So Arjun. Yeah, C section. Yeah. Yes. 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 Only bending. Yes. Yeah. Yeah, this point is not shear center. This is centroid. Yes, yes, yes. This one, web. Ah. Yeah, so basically, yeah, we have to, because see, this shear center depends on the geometry also. Actually, it depends on geometry. It's a geometric property. Shear, if we find shear center, it's a geometric property purely. So it depends on geometry. Basically, it depends on width of this web, depth of this web, width of the flange, depth of the flange. Okay. So based on that, it varies along this axis. How far it will go or how nearer it will be the web, it will depend from there. Okay. Yeah, how nearer it will be to the web or how far it will be to the web, it will depend on the dimensions of the web in the flange, basically the geometry of the cross section. Okay. So just like as professor had done a little protrusion and he has put a load, but in case of if we draw this the angle section, so if we actually find the shear center for the angle section, so he had mentioned also in the lecture, sorry, he had mentioned on the in the lecture, actually the shear center lies here. This is the shear center. Okay, but he said that you might go and check that it was very difficult for him to apply the load at this point, and that is why he put the load exactly here, not there. It was just a inconvenience in putting that load at that point, because he was loading through his hand through a pen, and the material he used was aluminum and it was very stiff. So he was saying that the pen, the tip of the pen was slipping at this point because it's just an edge. So instead of that, he put a protrusion here, and on that protrusion he put the load. So it was very near to the shear center, and that's why we couldn't see any rotation. But however, when he put along the centroid, you could see the cross section rotating. So in the same manner, if you load the channel section in this way here, you will see the channel rotating. It will rotate. However, if you will do a thing like you will protrude it and put a load here, it won't. Or if you will do the something different way, then if you change the orientation of this channel, then you will see. If you change the orientation, if you load like this, it won't. Yeah, though this will, then in that sense this will become the plane of symmetry. Yeah, so everything, that property got changed because we are treating the section in a very different manner. Okay. Yeah, so yeah, I think doubt is clear. Okay. Yeah, thank you. Okay, so now what I was saying, that let's write the formulae for the unsymmetrical bending, because it's a kind of very important formula, and I'm glad that the professor has given that full formula, because you can find the bending stress, that is sigma x, using that formula. Okay, and you can use this for any case, then whether IYZ is there or not, means basically if there is a unsymmetry in the cross section, as well as if there is an unsymmetry in the loading. Okay, so you can use in both the cases. I will show you, I will tell you what is the meaning of both. So the formula says that it is minus of YI YY minus Z IYZ into, I am just taking this formula from the, I have taken this from the lecture itself, plus y times IYZ minus Z IZZ into MBY divided by IZZ IYY minus IYZ whole square. And this minus is, I think, is a combined minus. Okay, this negative is combined to the full expression. Okay, not to the above only, it is to the expression, I guess. So okay, so in this formulae, what where is the unsymmetry in the cross section and where is the unsymmetry in the loading is coming, that. So till now we have seen the movement acting on a cross section about the ZZ axis like this. Okay, always we have seen about this axis MZZ, okay, or MBZ, like this. Everywhere we have done like this. Okay, but what happens if we have something inclined loading or some loading which will cause MBY? Basically we are getting a bending moment in this y axis also. Okay, in this axis. So he has included that term also. What happens if MBY is there? So there, this MBY and MBY and MBZ, here we are getting the unsymmetry in the loading. Okay, if there won't be any unsymmetry in the loading, then only one of the term will be there, either MBY or MBZ. But if both are present, that means there is a way somehow the bending is happening in both the axes. Okay, one thing. Another thing is we are seeing the term of IYZ. Okay, now this IYZ comes, as you know that IYZ is 0 for symmetrical sections. Okay, so this IYZ is 0 for symmetrical section, that means it exists only for unsymmetrical sections, sections such as like the angle section. Okay, that means this IYZ is incorporating the unsymmetry in the cross section. Okay, this IYZ is incorporating the unsymmetry in the cross section. So therefore, if you see that this formula or look at this formula will give you a overview. So whichever way you are using or whichever way you want to find, if you put it accordingly, you will get the results. So if you if you reduce this formula for the symmetrical bending, so I will say symmetrical bending, so IYZ is going to be 0 and MBY also we are putting 0. So if we do that, so what sigma x comes out to be? So it will be minus YIYY, this term goes to 0 into MBZ. MBY is already 0 divided by IZZ into IYY, and we get IYY gets cancelled, so it will be YMBZ upon IZZ, and this is the same formula which we use in our pure bending case. Okay, this is the same formula, minus a sigma of x by y is equals to MBZ by IZZ, same thing. Okay, that means yes, it is giving the subset cases. Subset cases like symmetrical bending with IYZ as 0, that means the cross section is symmetric and MBY is not present, only one axis of bending, bending is happening only one axis. So we are getting the same formula which we got for the from the bending formula. Okay, okay, so we'll yeah 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 yes 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 okay okay yeah. So see right now see actually what is happening, we have written this sigma x that is bending stress formula in terms of MBZ and MBY. What happens if I finally write the deflection equation? Okay, so basically what happens, the deflection also could be written in terms of MBZ and MBY. Okay, so when sir is applying a point load at this point, which is like putting load here, so what is happening due to this, because for this cross section you have MB this IYZ. Okay, so basically the symmetry is about this, this is the axis of symmetry kind of. Okay, this, so because it is passing through shear center, no, means basically it is passing through the centroid, and about this the section is symmetric. It is passing through centroid. Here there is a centroid of the cross section and it is symmetric about this. So what he has done, he has resolved this force into this and this. Okay, so if we go to the engineering mechanics course or the first level course on engineering mechanics course, there is something called principal axes also. So these are the actually the principal axes. These are not the principal axes actually, basically. Okay. Yeah. So because of that, if we draw in this sense, we get that we this force we do this means we take the component of this vertical load in along this direction as well as along this direction. That will now cause a MBY, because now you can calculate a MBY and MBZ with respect to that. Okay, so if I yeah unsymmetrical, yeah, it's an unsymmetrical bending. Exactly. Yes. And the best way to find out is using this way. We have to be reminded of these two quantities. We have to just look for these two things. Okay, whether the cross section is unsymmetrical. If the cross section is not symmetrical, even if you apply the load, the same thing as I told you. So here what is happening, the cross section is not symmetrical. Okay, but I am applying the load at the either you call shear center. Suppose I am ignoring the rotation, so I am applying the load at the shear center. Sorry. So due to that, what is happening? It is undergoing the unsymmetrical bending. Okay. Yeah. Okay. So we found that this formula is very general formula. It's a generic formula which we can use for the different cases. Okay, we can use for the different. Now the second thing which was discussed was the deflection. Okay, so deflection of the beams were discussed. Beams. So basically you found that finally the relationship between the deflection V and the movement. So we find that EI d square V upon dx square dx square is equals to MB. Okay. Now even as I told, so like maybe not in this course and further high level course, you may see that even this expression will be for unsymmetrical bending will consist of different terms. It will have MBY, MBZ terms and IY, IZZ and IYZB coming. But here professor has restricted only to the this thing. Maybe he may take it in further lectures, but for till this week's lecture he has done it for the case of symmetrical bending case. Okay, even this formula, because this formula as you have seen, it is coming from the same Bernoulli beam theory. So we can generalize this formula also to with respect to the unsymmetrical bending, and then we can find, we will say there is a deflection V and there is a deflection W in the other direction, and we can find both the deflections. Okay, by solving the two equations simultaneously we can find the deflection in both directions. Okay, so we saw this. And then we had the expression that V is nothing but minus of dm b by dx, and Q is nothing but minus of dV by dx. So if we derivate and substitute, so we will get d power 4 V by dx power 4 is equals to Q in terms of loading. So using this formula, because as you know that for there are two types of structures which we go through. One is statically determinate, another is statically indeterminate. In a statically determinate structure, only the equations of a static equilibrium, that is summation of force of all forces in x direction is 0, summation of all forces in y direction is 0, and moment at about any point in a plane is 0. These equations are sufficient to find the reactions basically, or to analyze the a given structure or a given problem, a beam or something, an axial member or something like that. But what happens in case of statically indeterminate structure, these equations are not sufficient. We need to bring in the concept of deformation also. So we apply some concept of deformation or displacement, and that is also called like we basically invoke the displacements and use them apart from our basic equations of static equilibrium. So that means, and that is not a part of the strength of material course. Okay, so basically it is difficult to find the reactions for those statically indeterminate structure, so we can't find the bending moment there. But if we use this equation, as you have seen in the lecture also, you can easily find the deflection, okay, using this, even for the statically indeterminate. But here you can't, because you can't solve the equation, solve the structure or find the forces without using the deformation concepts. So it is difficult to find the bending moment or shear force, even for that matter, or shear force also. Okay, but Q is a given thing, it's a given load, so you can directly use it there. Okay, so this concept was dealt, and then the concept was of moment area method was taught. So how we can find the change in angle, change in slope, okay, and then using that two theorems were postulated, and in that two theorems you see that how to find the change in angle and basically change in slope. I'm saying again angle, it's a change in slope, and from that then further how to find the bending moment. Okay, so let's go to today's problem. So we'll try to solve some problem on unsymmetrical bending and then some beam bending problem also. Okay, so I have chosen this problem just to give you the flavor of how even in a symmetrical cross section we can encounter an unsymmetrical bending case. Okay, so let's go to this problem. So a cantilever beam of rectangular cross section is subjected to a load of 1000 Newton which is inclined at an angle of 30 degree to the vertical. So you can see that there is a load, this load, it is inclined from the vertical at an angle of 30 degree. What is the stress due to bending at point D near the built-in end? So built-in end is called the fixed end is called the built-in end. So the point D has been specified, this corner is the point D, and it has been asked that what is the value of stresses developed at that point. Okay, so as I told you, even if the load is not on the plane or the axis of symmetry, it will be a case of unsymmetrical bending. As you can see, this is a symmetric cross section, it's a doubly symmetric cross section, but the thing is the load, which is this load, is not acting on the plane of symmetry. Okay, till now we have done the problems or analyzed the structures which were like this, the load was acting on the plane of symmetry, but now the load has been acting in a different way. Okay, so let's solve this problem. So what I'll do, I'll copy this cross section. Okay, so let's write the what is the width. So our width is 40 mm, 4 centimeter, that means 40 mm, and the depth of the beam is given 60 mm. 6 centimeter. Okay. Okay. Now what I will do, I will find the second the moment of inertia also. So what is first I will find IZZ. IZZ. So what is IZZ? 1 by 12 BD cube. Okay, this will be IZZ. So 1 by 12, B is the width is 40 into D is 60 cube. So what this value comes? Can anyone calculate and let me know? (72 into 10 to the power 4 mm 4). Okay, and similarly I will calculate IYY. So IY will be 1 by 12 D into B cube. Okay, 1 by 12, D is 60, B is 40 cube. So can you tell this? 32 into 10 to the power 4. Okay, mm 4. Okay, and as you know, IYZ will be 0. It's a symmetrical section, no? So for symmetrical section, integral, it is what? Integral YZ dA, so it will be 0. Okay. Okay. Yeah. What one can we consider? Okay. No, it's not. No, I don't think we can say in that sense like it passes through like this. Okay. I'm not sure whether we can say, means you mean to say why it is 0, you are saying. So the reason you are saying that it is because about the diagonal it is same because of that. I think that comes yeah. Okay. Yeah, what happens actually, we tend to do what? We tend to say some at y distance and z height, or some z distance and y height, we tend to have a very small area, basically delta A. Okay, and that delta A becomes delta y into delta z. So when you integrate it, it becomes y square by 2 and z square by 2 in multiplication. Now when you have to put the limits, your limits are minus, suppose this d, so minus d by 2 to plus d by 2, and your limits in y becomes minus b by 2 to plus b by 2, or the other way around. This will become minus b by 2 and this will be plus b by 2, and similarly this will be minus d by 2 and here d by 2. So because the limits are that, and it is an even function because it's a square, so it is like d square by 4 minus d square by 4, so it becomes 0. So, yeah, so I'll write it here. What happens basically, what we do, I'll draw here. So at a distance, I am taking this as positive z and this is positive y as given in the question. So we tend to take a very small area here which is at a distance of z and at a distance of y, and the width will be dz and the depth will be, means this will be dz and this will be dy. Now what I do, that what is that small area? That small area is dy into dz. So what we do, we say yz dy into dz, and it's a double integration basically. Okay, it's not a single integration, so it's a double integration, because here it is a dA, so I have changed the dA to dy dz. Now it's a double integration. So now what it comes, it becomes y square by 2 into z square by 2. Now I have to put the limit of integration. So for z I y so y is this, how y is varying, minus h minus d by 2 to plus d by 2. So I put minus d by 2 to plus d by 2. And how z is varying, z is this, so it is varying from minus b by 2 to plus b by 2. So minus b by 2 to plus b by 2. Now if I put those limits, so you know that it's a positive function, no? It will give negative value, also gives positive value. So d square by 4 minus d square by 4 becomes 0 in both, and other way b square by 4 minus b by square. So that's why it comes to 0. Okay. The other point you made, that whether about the diagonal we can judge it in that sense, I'm not sure. I have to look at that. Okay, I'll look into that and then I'll come up with an answer. Okay. Yeah, but with respect to how we find IYZ, that is the way to find IYZ. And in general, if the cross section is having, I think, at least one axis of symmetry also, so IYZ comes out to be 0 in general. Okay. Because see, why I am saying it is having if at least one axis of symmetry, because about one axis it will form this, and these are in multiplication. What I am trying to say, because suppose it is not symmetric about z, so this won't be like this, it won't be a limit from minus b by 2 from b by 2, it will have some different limit, but at the end it will have this same limit for y, and once this becomes 0, the product is 0. That's why this is also called the product of inertia. Okay, so that is why even if there is a single axis of symmetry, about that one quantity will become 0, and then because it is in multiplication, that goes to 0. Is it understandable? Okay, yeah, okay. So that is there. Okay. So in our case we have IYZ 0. Okay. Now let's look at the force. So you can see this force is inclined like this. So what I want to do, what I'll do, I'll translate this force from here to here. Okay, just for our convenience, I'll translate it here. Okay, so we can easily understand more properly. So I'll draw the cross section. Okay, so this is y, this is z, and from the vertical it makes 30 degree. So what I'll do, so this angle is 30. If I extend like this, so this angle should be 30. Okay, here, this one, correct? Yeah, this one will be 30. So here also this angle should be, I'll write as theta. Okay, and theta is 30 degrees, and this is my load P. Okay, now what I do, I resolve this load into two. So one I resolve in this, so this becomes P cos 30. Another I resolve this, which becomes P sin 30. Okay, correct? That's how it is going to be resolved. One is in the negative y direction, and another is in positive x direction, z direction, sorry, positive z. Okay, so and this load is acting at the end. Okay, you mind that end. So I am just resolving right now forces. I have to find the moment at this point, okay, because you know whatever equation requires, it requires moment. Okay, so right now I have just found the force at the end. Okay, this is the end cross section. I will write here end cross section. Okay, okay, okay. So now if you see, when this load, which is p cos theta and p sin theta, so when p cos theta will act, you know how that load is going to be, means it is acting vertical. P cos theta will act like this, and p sin theta will act like this. Okay, now when p sin cos theta will act like this, it will cause what? It will cause tension on the above. Okay, it will cause this hogging bending moment, it will cause tension above and compression in the below. Okay, so that means it will be negative, and we need to find the moment at this end. Okay, because our calculations are, we are now finding calculation for this point, so we need to know the what is the moment at this cross section. So okay, so what I will find using MBZ will be negative, and it will be what? P cos theta into the length of the this thing. What is the length? Length is 400 centimeter. So L, length is 400 centimeter. Okay, so let's substitute the value. So minus P is given 1000 Newton, cos of 30. Okay, into 4000 mm. So it will be minus root 3 by 2 is cos 30 into 4 into 10 to the power 6. Correct. So basically it will be minus 2 root 3 into 10 to the power 6 Newton mm. Okay, this is MBZ. Okay, because it is I have found the moment at this end, at this end I have found the moment due to the vertical component of this, and that is why this vertical component will cause a moment in ZZ, and that is why I am writing it as MBZ. Now what is remaining? The horizontal. This horizontal one will cause what? It will cause the this horizontal I'll draw here, this horizontal component of the load, which is P sin theta, will cause what? It will cause, yeah, it will cause if you see, it will cause a hogging again, because this it will make the beam bend about this axis first of all, but not this way, like this. This edge, which is behind, just behind this edge on the other side, so this edge will be in tension, and this exactly, and this edge will be in compression. Very good. This edge will be in compression, means the edge here which is visible to us will be in compression, and just the one behind this edge, the one just behind this edge will be the one in the tension. So again it is a kind of hogging. Okay, it is hogging. So we will write the MBY also. So MBY will be minus of, will be P sin of theta into L, same length is there. Okay, so minus of 100,000 to sin of 30 into 4000. So sin 30 is half, so it will be minus of 2 into Newton m. Yeah, okay, 2 into 10 to the power 6 Newton m. So we found MBZ, MBY. Okay, now we just need to apply the formula, okay, to find that. Okay, apart from that, we need to find, so I will write cross section at built end. I will first draw cross section at built end. Okay, so it will be something like this. this is positive y, z, positive y, and this is our point D. Okay, and this is the origin. So this is 60 mm, this is 40 mm. So this is the positive quadrant for both positive x, positive y. Here positive negative y, positive z. Here negative positive y, negative z, and here both are negative. That means this will be y comma, we have to write y comma z of this point. So y will be what? Y will be what? Exactly, minus 30, and z will be what? Minus 20. Correct. So we found the y and z also. What is y and what is z? Okay. Then let's move to our formula. That is the bending stress for unsymmetrical bending. So what I will do, I will write the full formula first. Sigma x is equals to minus there I y into I y minus z into I y z into m b z m b z, correct, plus y into I y z minus z into I z z into m b y full divided by I z z I y y minus I y z whole square. Now we know I y z is 0 in our case. So I y z being 0, this becomes sigma x is equals to minus y into I y y m b z plus z into, so it will be not plus, again it will be a minus something like that, I z into I z z m b y, okay, totally divided by I z z into I y y. Further if I will divide, so it will be minus here y into m b z divided by I z z. That is the formula which we have learned till far, we have done with this. Okay, and plus I will open the sign. Okay, what I will do, I will open the bracket, so there will be minus here, and this will become plus z into m b y divided by I y y. Okay. Okay, let's substitute the values. So minus y is minus 30, mbz. Okay, so mbz for us is minus 2 into 10 power to 10 to 2 root 3 minus 2 root 3 into 10 to power 6 divided by izz. Izz is 72 into 10 power 4. 72 into 10 to power 4 plus z is minus 20 and by is again minus 2 into 10 to power 6 divided by this is I think 32 into 10 power 4, 32 into 10 power 4. Okay, so this will be finally negative, so it will be minus 6 root 3 into 10 to power 3 divided by 72 plus 4 into 10 to power 3 upon 32. So again 6 this way So minus root 3 by 12 into 10 power 3 plus 1 by 8 into 10 power 3. So if you can calculate this value, so we can find the final answer. $269. Okay. Yeah, just check again. I think it should not come that high. Value should not be that higher. Yeah. Just check the calculation. Yeah, there is a negative sign here. So yeah, this one is a negative sign. Okay. Yeah, now this is lower. Yeah. So yeah, so minus 19.34 MPa, because everything is in Newton and mm, so it will be MPa. Okay. So yeah, we can say uh, we can say that it is in compression, the point T. Okay, because it's coming out to be negative. Okay. So if similarly we would have found somewhere else, maybe this point or this point, we could have found that it would be in some other value. Okay. So yeah. Okay. And also this is like in this case we are having a compressive value at this point. Okay, at this point, and anyway we are having a negative bending moment. So obviously if this MBY would have been 0, this would have been anyway compression. Okay. Okay, so this way we can find for any point. Okay, so if suppose we get a cross section where there is not a symmetry, the cross section itself is unsymmetrical, like I or some other cross sections. So in that scenario also we need to include the IYZ component in this formula. Okay, we need to make sure this component is make use of properly, and then we can substitute the value and find the answer. Okay, so the full derivation of the formula has not been given in the lecture, but like as I told, it's a very early course on mechanics, so it's an involved formula. But although professor have introduced it, it's a very nice way to understand that bending could happen in multiple axes, and in actually in real examples or in real life problems it happens in very different way. So as you might have remember the problem of Führer, that bone professor has shown in the lecture. So it's a natural thing. Now if you imagine how we walk and how we, when we run or when we do our exercise, how we put different postures in play when we do different exercises. So in that scenario, the same bone comes under different loadings, sometimes different kind of bendings as well as bending combined with torsion. So the professor solved it with very by assuming that torsion is not there or other axis bending is not present, but it could happen that in real examples different types of bending could occur. Okay, So in that way, this is very important formula. Okay, so this is the way to solve for this thing. Okay, now we'll do one problem on the deflection. Okay, so because deflection has been taken in the lecture, so uh, as professor has shown or given the formula also for many simple cases. So uh, because it's a first level course, so right now we don't need to worry about much complicated cases, because the restrictions is there with respect to the statically indeterminate one structure. So right now we are dealing mostly with statically determinate, and only for indeterminate we are using that uh, fourth order equation, where we will have four integration constant of integrations, and appropriate boundary conditions will be used to find the those constants. Okay, so what we will do, we will solve this problem for today's session, and we'll try to find out how we find deflection at different points. Okay, and as well as slope. So in this it says that to find deflection and slope at point P. So P is the point of application of this the end point of this UDL, and Q for a given beam subjected to a uniformly distributed load, use double integration method. So here we are using just simply the double integration method. Okay, okay. So you might have remember that in the lecture, or even if I ask you to draw the bending moment and shear force diagram, so you know that the bending moment till this region is 0, and then it starts reducing like this, and then becomes negative at this. Okay, again because there is a vertically downward load here, so obviously the cross the top flange of the beam, the top portion of the beam will be in tension, and the bottom will be in compression, and it will be a hogging movement. Okay, so what I'll do, I'll start with the bending moment in shear force diagram. Yeah, so if I draw the beam here, so we have the beam like this. I'll draw this just the center line of the beam. Okay, and we have the UDL here applied till length A, and this length is B, and we say that A plus B is L, total length is L. Okay, so this is Q, I think. Yeah, Q is applied. Okay, so if I ask to draw the bending moment and shear force diagram, so yeah, so you know that this load is UDL, so it will keep on increasing. So the it will be something like, what I'll do, I'll drop a thing. Okay, so something like this, a straight means a linear variation will be there. Okay, and the value here will be Q into A. Okay, okay, Q into A. Yeah, so then we'll draw the bending moment diagram. So as you know that this will cause a negative bending, and it will be what, Q square, Qx square by 2, that the bending at any section. If I do an x section from here, okay, because I know there is 0, this region is 0, no load is there, so I just need to worry from here, or I will check my x like this. So if we see, so it is nothing but Qx square by 2, that is a parabola. So the this will be parabola it will be a parabola actually. Something like this. Okay, it's a parabola. Yeah, and it will be Q A square by 2 here. Okay, Okay. So now we need to find the deflection as well as slope. Now our point of interest are this P point, this is the P point, and this is the Q point. These are the point of interest. So as you have seen in the lecture, when professor has done that experiment, when he puts a load here, so it the elastic curve or the deflected shape, let's call it the elastic curve or the deflected shape. So how it looks, let's see that also, how the deflected shape or elastic curve looks. So if suppose the load is applied exactly, or I'll draw for the current case where there is a UDL. So what happens, the till this point, that is till this point, the beam is under, the beam has a curvature, elastic surface, it's a curve, okay, like this. So I have drawn a little this, and then after this it's just like a straight line, just like a straight line, okay. That is the point, this point is important. After this it's just like a straight line because it doesn't have any bending movement in there, okay. So exactly, so it's like a rigid body rotation. So because it's just rotating, because the other part of the body is connected to it, the other part being this part, so this part is connected to it, so it has to just follow it, but this will not have, this portion will not have any curvature. This portion will have a curvature in the beam, but this portion won't have any curvature, it will be a straight line and it is just a rigid body motion, okay. So now we know how to find the deflection here or the rotation angle theta, okay, at this point to draw a tangent and find the theta. So we can do that, but to come at this Q, which is also our point of interest, at this, how to come up with this deflection and with the theta at this is that, so what we do, we actually find theta here first of all. So what we do, we draw a horizontal line here, and actually after this line, with this line which is extending beyond this point, is actually a tangent at this point itself to the elastic curve, this curve. As I told, this will become a straight line, so this line acts as a tangent to this curve at this point. Hence we found the theta, which is the slope. So we use that slope, and what we need to do, we need to find this much value, because this much deflection is already at this point. We know this much deflection, which is same as this here. So we know this deflection here, we need to only find this much deflection. What is this? So to find that, what we do, we multiply, we say that this is very small, because see, as professor has told, this means a small deformation, we have always theta less than 4 degrees, 4.7 degrees or less than 5 degrees. So for so lesser amount of angle or very small angle, we can say that to find this length, this can be an arc, this length being a straight could be an arc. So to find an arc, what we do, we multiply this length with this theta. So to find this length, what we do, we multiply this distance with this rotation, we get this value, and we already know this much deflection, so we add to that and find the total deflection, okay. So this is one of the very important questions they usually ask in competitive exams also. So that's how we have to perform this, okay. Now our full focus will be to find what is the deflection as well as slope of this point. If we are able to find the deflection as well as slope at this point correctly, then we can very easily find the value of theta at the Q point, theta and delta at the Q point, okay, okay. So okay, so what we do, we say EI dou square V by d square dx square is equals to m b z, okay. That is a one moment, okay. So if you look at this, what I do, because I am assuming this as my origin 0, okay, this is my positive y and this is my positive x, okay, and this is the point is origin. I will mark as red. This point is origin. So I will write with respect to that the this thing, the bending moment, okay, because I want to do it in that sense, okay, considering this red mark as the origin, okay. So what I'll do, I'll draw the free body, okay. So in the free body, I cut it actually from the main body, okay, from the support, okay. So we don't show the reactions at the support, we show just very near to the support. So I will have a reaction here, okay, and we know to find it out very easy, just to do what, this load q multiplied with this distance, that will be the reaction, okay. So that will be qa, q into a, okay, and the UDL is also acting like this, okay. So at any point what will be the bending moment? MBZ is equals to, so this QA will be a positive, it will cause a sagging, not hogging, QA. So it is positive QA. So I will write QA into x, at any x I am writing, okay. Then the downward load about this point, the downward load, this downward uniformly distributed load is causing a hogging actually, okay. So what I will write, minus of q into x by 2, x by 2 is at the centroid. So we assume that the UDL, full UDL is acting at the centroid. So what it comes, qa x minus qx square by 2. Now this is the MB for me. So just I will do what, I will substitute this here in equation 1, okay. So what I get, EI, and I am assuming E and I are constant, okay. We are not taking any case where E or I varies, okay. So QAX minus QX square by 2, okay. And you know that the bending moment is away, past point A is being 0, okay, is after this point the bending moment is being 0. So I am just writing this equation for the vicinity of x, I will mention. So what I am doing actually, I am writing this for greater than 0 x and less than equal to a, okay. I am writing it till a. After a I will see how we develop, okay. Till a I am writing right now, okay, because till there only we have moment, after that it is 0 moment, okay. Okay. So now let's do the integration. So we have EI dV by dx is equals to QA x square by 2 minus q x cube by 6 plus C1, correct, C1, correct, that is the integration, okay. And one more time we, yeah, Arjun, you had a question, oh that's fine, okay. EI, now I am doing one more integration, so I will get V, so it will be Q A x cube by 6 minus Q x to the power 4 by 24 plus C1x plus C2. So I integrated one more time, okay, correct. Now I need to find the constant of integration C1 and C2. How to do that? We need to apply boundary conditions. So I will look at boundary conditions. What are boundary conditions? So we know that this is a built-in support. Now we know that at built-in support, as you have seen in the lecture also, when professor put a load here or at the tip also, the deflection as well as the slope at the built-in support is 0. We have seen that. That means we know the boundary condition. What are the boundary condition? V at x is equals to 0, that is the built-in support. V is 0, deflection is 0, and dV by dx at x is equals to 0 is also 0. The slope is also 0 at that point. So we have two conditions and we have two unknowns, C1 and C2. Let's put it there. So first I will put the second condition, this condition, dV by dx at x equals to 0 being 0. So where I will put in this equation here. Okay. So I put that as 0. So if I put here x as 0, this becomes 0. This is already 0. So C1 comes out to be 0. C1 is 0. And now if I put this condition, the other condition in this one, so x is 0, so this is 0, this is 0, this is 0, this is 0, so C2 also 0. C2 is also 0. Correct? That means the equation becomes EI into V is equals to QA x cube by 6 minus Q x power 4 by 24. Okay. This is the equation for deflection. And similarly the equation for slope is EI dV by dx is equals to QA x square by 2, QA x square by 2 minus QX cube by 6 minus QX cube by 6. So this is for slope. Sorry. Okay. Okay. Now what I wanted the deflection at P. What is P at x is equals to A? So I just need to put x is equals to A in this one. So I will put EI V is equals to Q. I will put x is equals to A, so it will become A to the power 4 divided by 6 minus Q A to the power 4 divided by 24. So we find out this as 24 3 Q A power 4, that is Q A power 4 by 8. Correct? So V becomes Q8 power 4 by 8EI. Okay. So this becomes deflection. Similarly, slope. Is equals to A. So I put EI dV by dx is equals to, now you know that dV by dx is also known as theta. Professor has mentioned it as phi also, but also theta. So I prefer more for theta. Okay. So EI theta is equals to, now we'll use the formula and we'll put A with where the x is there. So Q A cube by 2 minus Q A cube by 6. So if we do that, so it will be Q A cube by 3. Okay. Yeah. Yeah. and theta will be qa cube by 3 ei. Correct. So this will be theta, this will be deflection. Now we will go to the point Q. Now our concern is Q. So as I told, I will draw it here again. So we have something like this, and from here it will be just a straight line, as I told, till here. Okay, this is the point. So horizontally this will be what? This will be till here, it will be VP. I will call P, that is the point P. Okay, and this we will calculate. Okay, so V at Q will be VP plus theta P into the distance, and that distance is B. This is the distance, so this is B. Okay, so Vp is already known, Q e to power 4, Q e to power 4 upon 8 ei plus this is Q a cube upon 3 ei into B. So this becomes VQ, and so this is deflection. Okay, and slope, as I told, it's a straight line. So slope at theta q, that slope will be same as theta p, and will be q a cube upon 3. It will be same because it's a straight line. Okay, it's not undergoing any bending. Okay, so because it will be a straight line, we will have this. Because it will be a straight line, we will have the same slope. Okay. Okay. Yeah. So that's how we'll find the slope and deflection. And integration method or double integration method is one of the most versatile method. And once we understand how to use, which way to use the equation for deflection, then it becomes very easy. Okay, and very easily we can find the deflection as well as slope. Okay, and even we can draw the elastic curve. So basically, what is elastic curve? This equation is the elastic curve. This equation. This equation is the elastic curve equation. Okay, so we can even draw. So you can even use an Excel sheet to draw the deflected shape. You can take some value of E and I. Okay, some cross section E you know for steel, so that you can take, and I you can take for some I section. So you can make a I section. Okay, you if you are exposed to some steel table, so you can just take any I section from steel table. You will have that IYY IZZ value. So just in Excel, you need to put the value of this E and I here. You means basically you divide this EI with here both side. So here it will be 6 EI and here it will be 24 EI, and then just use that to find the value of this V for X. So you can vary for your X from 0 to like 10, and then you can plot the whole thing. So you can plot the V with respect to X. So you will find the deflected curve of this like being like this. So in this case it will be something like this, and then it will be actually a straight line like this. Okay, so you can even visualize the elastic curve, and this equation is known as the equation for the elastic curve. Okay, yeah. So any doubt in this problem, any question here? Yeah, 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 yeah. So yeah, so what I would suggest that first you look at the problem and check which way you can do it very easily. Okay, whether the moment formula is easier to solve or the go to the loading formula. So wherever if suppose it's an indeterminate structure with UDL, then you can't use moment formula because you don't know how to find bending moment. So you have to invariably use the loading formula in that scenario. Okay, whereas if it is a determinate structure, now you have a choice. So suppose if in a determinate structure it is a 2 point bending, suppose may not be the point of bending are samely put, they could be put at a different or uh, 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 distances, not equal distances, not a exact 4 point bending, it could be a 4 point bending with different distances. So there the 2 point you can't use the q because you don't have any q. What I meant, like some scenario where you have a suppose a beam like this and one here, another here. So now you can't use for this case the q equation. Anyway, you have to go with the deflection. So basically, you go with that specific parenthesis thing. Professor also showed it, x minus a kind of thing. Okay, so you use of that, or you other way you can define the bending for, means you can find MB value for each case. So like you have a roller here, you have a loading here, so you write the MB for here, you write the MB for here, and you write the MB for here, and then you define your deflection for this region and this region. But when you integrate, you have to come up with the condition that at this point of loading, the deflection will be continuous. Okay, it could not be that the deflection of this one and this one will be different. So you need to make sure that deflection is continuous at these points. Okay, it should not change. Okay, so that we have to take care. But yeah, if it is as far as I know for this case, if it is an indeterminate structure, so you will be given a q loading only, because otherwise you can't find the moments. Okay, that I think. Yeah, yeah, so that is there. Okay, yeah, and like one very small thing also, like I can tell, like because this is very usually I'll just give a hint. Okay, I'm not sure, I'll just give a hint so that you guys can understand what could be asked. So even so, if suppose I will give you a beam and let's say, yeah, not this. Okay, it's a cantilever. Okay, it's a cantilever, something like this, and so okay, so suppose it is being asked like this, q, it is being applied in this region, we call it as again B. So here q is applied, this is A. Okay, so what is the quickest way to solve this one? Okay, so one way could be, what we can do, because we are living in principle of superposition world, so what we can do, we can make the same beam like this, and first what we do, we load it fully like this. Okay, and then what we do, we make a similar beam, okay, like this, but with this much of opposite loading. Oh, sorry, this much of opposite loading till here of q. So now what is the resultant of these two? This is the resultant, the above one. So if you know the formulae for this one, this is a very general case. This is a general case, no? So if you know the formulae for this case, you can very easily find for the deflection wherever it is asked, because you just need to do subtraction from one to another, specifically because most of the time the deflection is asked at specific points like this point, or in between, middle point, like that, or maximum value of deflection. Okay, so what if somebody asks the maximum value? So what if somebody asks the maximum value? So what you need to do, you need to have this elastic curve, okay, this curve, and you need to do what? You have to just basically, how we find a maxima, we differentiate that and put it as 0. What is the differentiation of this? This slope is the differentiation. So if you put, and you have also remember from the example which professor showed, the first example of a simply supported beam with a UDL, you saw that the slope at the midpoint is 0 because there the deflection is maximum. So everything is interrelated. So if you put this as 0, you will find a value of x. That value of x will be corresponding to the maximum value of deflection, and when you put that x here, you will find the maximum deflection. Okay, and suppose if somebody asks the maximum slope, then you have to differentiate this equation one more time. You differentiate this equation one more time, you put it as 0, find the value of x, you put that value of x here to find the maximum slope. So it could be asked in that sense also. Suppose the elastic curve equation is given, means maybe they would give this equation, elastic curve, okay, and then they could have asked at what point of x the maximum slope will occur, those kind of thing, okay, or like something like that, okay. So like that, in that sense it could be asked, okay. Yeah, achha. हाँ, yeah, yeah, yes, हाँ, yeah, okay, we can call it, but the thing is, traditionally, like historically, it has been called a 3-point bending when it was at the center, okay. But yeah, even if it is 3-point but not at the center, it will be a 3-point bending. It's not a issue. Yeah, yeah, yeah. That formula is only applicable when the load is at the center. It has, yeah, as soon as this load moves away from the center, you can't apply the same formula. You have to find the deflection differently, okay. Okay, so if suppose we have this, so if this is there, P is acting like this, you can't do that, okay, then you can't do, then you have to find different, but yeah, if only one load here, like only P load is acting, that is the point load, and that is only that load is acting, always the maximum deflection will be below P only, that is true. Now you move anywhere P, this will be true, the maximum value will be always below this. So as soon as the only one load is acting, if you increase more than one, suppose now you say, sir, will it be applicable for this case also? So suppose I draw this one like this, so 100 kilonewton load, and then here some 400 kilonewton load. Now you say whether it will be below 400 or below 100. No, I can't say now, because there are two different load, so we can't say where it will be. Then you have to just find the elastic curve, differentiate it, find the value of x, and then put it, then only you will be able to find. But for a single load, when this load is not there, obviously the maximum will be below this, okay, and suppose this won't be there, so it will be below this. So in this example, it will be below this. Wherever if single load is there, the deflection will be below just that only, okay. Yeah, yeah, Yes, yes, yes. No, no, no. Yeah, then they have to. It has to be different. It has to be different. Yeah, the value will be different. Even if I would say even so, uh, if you see, it will be different in a sense. Okay, so it is actually related to BMD. How BMD comes. Actually, it's very interesting because when we go to there is a concept which we usually teach in civil engineering courses, and it comes in the it's a third year course or something. There is a concept called moving load. Okay, so I don't know whether in other engineerings like in mechanical or aerospace or applied mechanics, I don't know whether it is being taught, but if specifically in civil engineering mechanics it is taught the concept of moving load. So actually what I'll do, I'll tell about this. Suppose there is a load and I'm taking this as a simply supported. Okay, it's a simply supported thing. Okay, so suppose this is a load and this is length A and this is length P. So usually this reaction will be Pb by L and this will be Pa by L. Okay, the reactions will be like this. Now if I draw the BMD, I will draw sideway. Okay, here I will draw. So the BMD comes like this. Okay, so it is PAB by L, the the moment value M. Bending moment value, that is the maximum value, is PAB by L. Now your A and B are variables. Okay, your A and B are variables, and actually A and B are fractions of L. Okay, you can say A and B are fractions of L. Okay, fractions of L. Now their maximum value occurs when you are at the center. Now let's have an example. I say that A is L by 3, B will obviously 2L by 3. So what is the value of AB? It is 2L square by 9. Okay, just calculate using your calculator. What is 2 by 9? What is 2 by 9? 2. Okay, now I say A is sorry, I'll write it. A is suppose L by 2, then B will be L by 2 obviously. So AB is L by 4. It is 0.25. So now you vary. Okay, you can vary the A and B in any fraction. A could be L by 4, B could be 3 by, let's try that also. A could be L by 4, B could be 3 by 4 L. AB will be 3 by 16. Can you find this value? 3 by 16? 1875. So you can see only when the A and B are equal fractions, the value will be of the product will be maximum. When A and B are equal fractions. Okay, that means the maximum value will occur at the center. That means if your single point load is away from the center of the beam, center as the lengthwise center of the beam, so the deflection will obviously be maximum at this point only. But what if I would have put my load at the center of the beam? The deflection value here, as you rightly told, is minus WL cube by 48 EI. Now if I put here and suppose this deflection is suppose V, I will say V 3 by 4. Suppose that value is V 3 by 4. Your V 3 by 4 will be less than this. V 3 by 4 will be less than the value when the same load would have been at the center of the beam. because this is the maximum deflection if you try to move the load along the length from this end to this end. If you try to move the load at the center only will be the maximum value. If you put anywhere other than that, it will be maximum for that position of the load, but not the overall global maximum. The overall global, if I ask you what is the maximum deflection a simply supported beam can have for any configuration of position of a point load, then I have to invariably put at the center itself. That is the answer. That's what I am trying to say. If suppose I give you a choice that you put as per your own choice the load, wherever you will put I will consider that point, but I want what is the maximum deflection. So maximum deflection will occur only when I will put the load at the center, and that deflection will be maximum of all the cases if I am moving like this if I am moving. How I came to that conclusion? I came to that conclusion from the bending moment. We know the deflection depends on bending moment. We have just seen our equation, how it is made. It made in terms of bending moment. It depends on bending moment. These properties are constant. E and I are constant. Limit of integrations are constant for a beam. So what it matters? It matters the bending moment. And how bending moment change we have seen. So if the fractions are equal A and B, then only the bending moment will be maximum, and that happens at the center. Okay, is it clear? Yeah. So as you move across, so like you make different triangles like this. So basically actually this if you trace the path of this thing, if you trace the path of these maximas of each case, if you trace the path, they themselves comes as a parabola. Actually they themselves comes as a parabola, and the maximum value of the parabola comes here at the center. If you just trace the path of these maximum values, okay, they themselves comes as a parabola. Yeah. Yeah. It's like, so you can imagine, like just imagine like you put two bricks, okay, two bricks some distance apart, and then put a wooden a wooden plank on it, and then first start standing at the center. You stand at the center, you will see that both are making equal, like bulging in the same way or bending in the same way. Now as you move towards any of the support you will move towards will bend more, will have more depression. Exactly as you said correctly, there will be more slope here. So if I draw the elastic shape or elastic curve, so it will be something like this. So because it will have higher deflection at this point, should have highest deflection, so it will be something like this. It will have very less slope here and very high slope here. If you move this point P here, then this end will have more slope and this will have less slope. Okay. Yeah. Yeah. Okay. Yeah. 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 Like you are saying stresses like in this direction? Yeah. 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 Yeah, so actually if we look in a practical sense, if we talk about practice, so basically you are asking whether this because this end is roller here, so even if some force exists in the x direction, this roller will move and there will be no stresses in the beam, axial stresses. But if it is a fixed beam, so there is no motion allowed, so obviously some stresses in the axial direction will develop. Now, yeah, 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 yeah. Okay, yeah. So like different things have different purposes, I would say, but what happens? They have different applicability also. Okay, so what happens that we have to think in a different manner, that where we can use what and where we can't use, where we can use roller and where we can't use roller. Now the point being, this stress is being developed. So as you can see that the only stresses we are acting or being applied externally are vertical. There is no horizontal force. So it should be in a horizontal equilibrium. So if I say theoretical point of view, there won't be any stresses. Okay, theoretically I am saying, until you are considering it as a 2D case. Okay, okay, but when you bring in the 3D case, okay, when you bring the other dimensions also, then it is a different story. Okay, then it could also have some stresses. Okay, so there is something called strength of material solution of a beam, there is something called elasticity solution of the beam. So right now the elasticity solution is a different way. So there the question that the problem is put as a boundary value problem. It's way higher than this this course of strength of material. I can't go into that, but yeah, you may have certain displacements or stresses developed in that direction also. Okay, but right now we are focusing here only on this part of this only. Practically also, when you come up with some beams and all, so you see that some of the stresses will be there mostly in this region practically. Okay, now about the usability or which one is good. So obviously if you are making a structure, obviously first of all most important is the restraint. Like we are drawing it very easily, it is very easy to put these bars and say that it is a fixed end. Okay, but how to achieve it in reality is more difficult, because we have to provide that much rigidity for this to have a zero slope for a considerable length. You have seen that the deflected profile is something like this. So for a considerable length the slope is zero. So to build that profile, to have that rigidity at this supports, it's very I would say very important to make sure that it acts as a rigid. Because if I do analysis, design everything considering this as rigid, and at the time of construction I failed to make this as rigid, then it will be a catastrophic, because you made it to have certain movements and shear force, but the movements and shear force which will come will be very different, then this support will fail. Okay, so that is one of the thing, the constraint in making the rigidity of the joints, and which is very like I would say very concerning things. These are very things of very important concern, because these are called connections some in a way, and connections are the weakest link in a structure if you see. Okay, first So that is from the usability point, one point. Another point is, if you are making a structure which will be subjected to too much of environmental loading, okay, by environmental I will say freeze and thaw or temperature loading, okay, or lack of fit cases. Lack of fit means, so suppose you constructed a beam, so I will give a very small example. So suppose this is a truss, okay, it's a 3-member truss. So what I said, it has having a load this. I analyzed the truss, I found the length of each member, all this member, okay, and I asked the fabrication person that you fabricate this length, this length, this length. I gave the dimensions. He fabricated and brought it to the site where it was to be assembled. Now while we were assembling, I found that this edge was a little bit longer than what was my requirement, say by 5 centimeter. This edge was longer by 5 centimeter. So that means it is not coming as a fit. So you have to and usually we at the fabrication, I am talking in a civil point of view. So from a civil point of view, usually we don't now it is 5 centimeter is very less. You can't cut it with 5 centimeter precision at the site. You can do that precision with using some machines or some good tools at the fabrication shed area, but not at the site. So what and it also it costs, it takes time, so there is a loss. So what the designer, what the site engineer will do, he will say, okay, put it there. Now because this being a statically determinate structure, it's a statically determinate structure. So what will happen because of that lack of it? So as per our calculation, the length of the member has been more. What will happen? This roller will move little bit and there will be no stress will generate. But instead of this having a statistically determinate truss, if it would have been a statically indeterminate stress, because of that lack of it, each member will generate some stresses. So that means now your structure, which was supposed to at the time of construction a stress free structure without the loading has been started, it should have been a stress free, but just because I introduced a lack of fit member, it is now experiencing a stress which is before the loading, and which is not good, because there is a preload. It is not a stress free or load free configuration without a load. Without this load, it should have been zero stress every member, but now it is not, because I am using a indeterminate structure. So that is I would say a bad thing, because now you have to manage for it, okay. And okay, tension is no, so truss is a uniaxial member. No, only axial tension or axial compression will apply. Okay, tension won't cause a issue. Tension is a very good thing. Wherever tension comes, it is a good. Issue is with compression. So now if compression comes, there is something called buckling. So if that compression exceeds due to that lack of it, then buckling could occur. We don't know. Then buckling could occur. So this is also one of the drawback of using indeterminate structures. Okay, so if you look at all the old bridges, if you come across any bridge, okay, important old bridge, you will see they have made it as a statically determinate. They don't make it aesthetically indeterminate. Nowadays we are having suspension bridge, other bridges which are a little bit complex to analyze and all. They are little bit statically determinate, because one thing happens in statically determinate, which we will see, maybe I'll talk it about in the next lecture, that our bending moments, if you go and back and check the bending moment in a statically indeterminate, or the deflection, if you check the deflection, what is the deflection of the same beam with UDL and of the same beam with the statically indeterminate, this fix, you will see the deflection, maximum deflection is lower. It is lower in the statically indeterminate, in a fixed beam, compared to a simply supported beam. That means the deflection is coming lower at the cost of restraints you are providing at the ends. That is the cost. Okay. So if you are having a way to provide these supports or these connections very properly, and their rigidity is proper, then it is good. Then it is good because you are able to reduce the deflection, and in a I would say in another sense your cross section dimensions will be lower. Okay, your cross section dimensions will be less if you design a same simply supported beam. Your cross section dimension in the fixed beam will be lower. That means you will save on material, but you should have the appropriate arrangement for the supports. Okay, and then some places this so you know that there is a rotation here. Okay, there is a slope here. That means it will rotate at this. This is a rotation free point. Now, so suppose I have a roof. So this is something roof. So in this kind of structures, these are our primary beams. I am saying PB, primary beams. These are primary beams, and these are secondary beams. Okay, so if I put a primary beam here, okay, and if I put my primary beam as what? As a simply supported. Suppose this secondary beam is a secondary beam. This is my secondary beam. This is my secondary beam, and if I suppose make this secondary beam as a simply supported, so what will happen? Will there be a movement at this point? There won't be movement, no. So means this edge and this edge won't be movement, but they will rotate. That means it will rotate, and that same rotation will be passed through this second primary beam. What if I make this secondary beam as fixed? So this will be fixed, this will be fixed. That means there will be a movement. Now this movement will be a point movement to this beam. This movement will be a point movement to this beam, and I have to analyze. I have to put extra some arrangement there to resist that point movement at that point. Okay, but if rotation will be allowed, then it will be allowed to rotate here. Okay, so then it will rotate there. So these type of things come up. Yeah. 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 So even in simply supported, very rarely we make it fully simply supported. Most of the time we make it as a propped cantilever. So we fix one end and we put some roller or put some hinge at the other end. We try to make it that. Because again I will say, if you compare the deflections with respect to this cantilever, you will find that they are way different, way less. Yeah. So basically these are the kind of design aspects, and in mechanical aerospace I would say it is most on the machine side. So machine design or designing in the machine is more concerned. But if you come to civil structures, then with respect to structure, these are more, I would say, more prominent, because you see, if you look about this length, no. So if you just imagine about the length. So if you imagine a building, these length of the beams, this length, they will be more compared to the machines. Most of the machines, they have higher, means what I am trying to say, the stress generated in machines or the components of the machines are way higher compared to the stresses generated in a normal structure, building structure. So there the and the precision is also very very important. The precisions in machine, that it should be 1 mm precision or 0.5 mm precision. Precision wise is very important there. In general structures, it is not that precision to 1 mm or 0.5 mm. It is precision, having precision in 5 mm, 10 mm. That's the precision there in the buildings or the civil structures. Okay, and also the dimensions of the machines or the components of the machines, most of the machines are way smaller than compared to the dimensions of the structures, building structures. So truss bridges or truss girder or the girder of the bridge. Girder is also a term for a beam. So that girder is way more bigger. So that is kind of a difference. Yeah. 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 Exactly. Yeah. 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 Basically, yeah. So they have something called uh, uh, there is this bearing where it's like where the bridge deck is supposed to attach with the pillars or the columns you see of the metro. So there they have columns, and columns above they become bulky, they become wide, and then on that wide the beam or the girder or the box girder sits on that column. So that column where it touches that column or the cap of that column, there some material, because if you directly put in touch it will just like crack the concrete, so we can't do that. So there are some materials, these are called mostly bearings, their general term is bearing, and they're elastomeric in nature, means like they absorb kind of load and then they distribute that load. So those bearings, elastomeric bearings are provided. So the bridge deck or the box girder is in contact with the bearing, and then bearings distribute the load over the this thing. Now there are different types of bearing also. One bearing will give only in the axial in one direction, the means it will allow to expand or stretch the structure in one direction. Another will give you into both direction. Some are called multi-axial bearing, so they will give you in all the directions. They will have a very little tolerance, like suppose 2 mm, so it will move in both direction 2 mm. So your design has to be appropriate that it should not move beyond 2 mm. So like that things are there. Yeah. Yeah. So I hope, yeah, you understood today's problems. Okay. Yeah. So we'll see some more problems. So one announcement is there. Mostly, actually, I will be traveling for next week. So I think mostly the next week lecture won't be on 9th, but yeah, I will do it later. So after 9th, I think we have a session on 16th. That is the last session. So I have to do, I think, it before 16. So mostly I'll be back on 14. So I think I am planning to put that session on 15, that is Sunday, same slot 6 to 8. I think, is it fine with you guys, because I have to do it before 16th. Is it fine? Yeah, because I'm not available on 9th. Yeah. 15th, yeah, 15th 6 to 8. It is a Sunday, so 6 to 8, and then next session will be on 16th. 15th will be 6 to 8, the 9th session, and 16th session will be on the same date. So, yeah. Yeah, that's right, yes. So, I want to do, because I'm not available in the week. So, yeah. So, yeah. Okay. Huh. Okay. 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 So one thing you do, that you just ask this from the first, you ask from the through the portal. Okay, through the this thing, and we have our last session of 16. So what I will say, you ask now. Okay, let's see what they reply. Okay, if they don't, if they say they can't do that, or they can't provide that, or whatever was the assignment is the practice for you, let me know by 16. Okay, you confirm it me to by 16, and then once that has been decided, the conclusion has been come, you let me know. I will do on my one, like from my side, if they don't do from their side. Is that fine? Yeah. Yeah, gcbridani@gmail.com. Yeah, that is my email. I'll write it again here. Yeah, 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 yeah. Even calculator also, but what I know about calculator, it is there in scientific calculator in the system itself. Yeah, so you can use that. So let me know by 16th. I'll otherwise I'll share with you guys. Okay, 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 okay. Thank you. Okay, thank you for today's session. Thank you all for joining.